In this lesson, we'll add loads to the assembly and learn more about how load cases work. Then we'll assign a material and learn how to modify its properties. As a load, we'll use a force that pulls on the bracket holes. Start the force command. In this command, you can select faces, edges, nodes, rods, and rod nodes. The selected objects are distributed among the corresponding fields. Select the cylindrical faces of the bracket holes. Then we need to define the force direction. We can use the Get Vector from Edge option and select an edge. The force will act along this edge. You can reverse the direction if necessary. Another option is to define the direction manually. Enter values to the component fields. In your case, set the X component to 1 and the Y component to -1. The force magnitude is automatically calculated based on these component values, but it's too small. Let me enter 3000 instead. Confirm the command. The component values are recalculated automatically. Note that values can also be entered in exponential notation. Since we don't need any additional forces, exit the command. The force appears in the load case 0 section. This load case is created by default. All newly created loads are added to this folder. If you need to analyze different loading scenarios, to evaluate the behavior of the structure under various conditions, you can create a new load case. A new folder appears in the tree. To make all new loads be added to this load case, right-click the folder and select Make Active from the context menu. Let's add another load. For example, we'll apply a force acting normal to the upper plate face. It will be 3000. Confirm and store the command. This force appears in the load case 1 folder and is independent of the loads in load case 0. Therefore, analysis can be performed separately for each load case. In the first load case, only the force applied to the holes is considered. In the second load case, only the force applied to the plate face is considered. We don't need the second load case for our analysis, so activate the default load case and delete the load case we created. Now let's move on to the next stage of preparation for analysis. We need to assign a material. Every model always has a material assigned by default, even if you have not specified one yourself. It's displayed in the Materials section of the tree. By default, this material is steel. You can modify its properties. Double-click the material in the tree or use the Edit command from the context menu. To add a new material, click Material in the Properties toolbar. Enter a name for the new material, my steel, for example. Adjust its properties. These properties are used during analysis. If you need a more complex nonlinear material model that accounts not only for linear elastic behavior, but also for plastic deformation, click Change. A window with additional properties appears. These properties are required for nonlinear analysis. This functionality is available in the professional version. We don't need it now. When you're satisfied with the material properties, click OK. Select the objects to which you want to assign the material, or you can click Assign to All to assign the material to all parts. Confirm. The system informs us that the selected objects already have a material assigned and asks whether the new material should replace it. I agree. The material folder now contains two materials, the default material and the new material. When you select a material in the tree, all objects assigned to that material are highlighted in the graphics area. The default material is no longer used, so we can delete it. The material name has changed because we changed its properties after it was renamed. Let's fix that. You can create multiple materials and assign different materials to different bodies.